everyone, welcome to my class. Hope you all are doing great in your life. So today we are going to start a new chapter, that is force. Okay, so without wasting any time, let's start the class. Students, in our earlier classes you might have learned about force and its effects. One of the effects of force is it generates motion. Okay, so whenever a rigid body which is free to move is acted upon by any kind of force, there are two kind of motion. One is your linear or translational motion, and second is your rotational motion. So now we are going to discuss about these motions in detail. Okay, students, whenever we apply force on a stationary rigid body, then the body starts to move in the direction of application of force, and it moves in a straight line. That is why it is called a linear motion or translation motion. For example, in this diagram, suppose this is a ball which is kept on the surface, so it is free to move, and if force is applied in this direction, suppose I push the ball in this direction, what will happen? In which direction the ball will move? The ball will move in this direction, isn't it? So the ball moves in the direction of application of force and in a straight line. That is why it is called your linear motion. Okay, linear motion. Okay. Students, when a body is pivoted at a point and force is applied at a suitable point of the body, then what happens? The force generates a turning effect. That means the body rotates around the pivoted point. So this motion is called your rotational motion. As you can see in this diagram, the body is pivoted at this point. Okay, suppose I apply force over here at this point. So what will happen now? It will not move in this direction. It will not follow the linear motion because it is not free. So what happens now? It creates a rotational motion. So the body will rotate like this around this point. Okay, so this is called your rotational motion. Students, let us now discuss about the moment or turning effect of force. Okay, suppose there is a body like this. Fine, and it is pivoted over here. Fine, suppose this is pivoted and force is being applied over here in this direction. Fine, this is the direction of application of force. So what happens over here? Let this force, as it is a perpendicular force, okay, so suppose the point of application of force is A and it is extended up to suppose P. Okay, so the force is perpendicular, but does it move in this direction? No, it cannot move in the direction of P. Why? Because it is pivoted over here, and we have already discussed that whenever the body is pivoted, it cannot go for the linear motion. So what will be the motion then? Suppose the point at which it is pivoted is O. So here it is pivoted. So it cannot move in this direction, but it moves in this direction. That means it follows a rotational motion. Okay, this is the turning effect of force. That when a body is pivoted somewhere, if we apply force, it doesn't go for the linear motion, rather it follows the rotational motion. Okay. So let us now discuss the factors affecting the moment or turning effect of force, which is also called torque. Okay. Students, the factors affecting the turning of a body are the magnitude of the force applied and the perpendicular distance of the line of action of force from the axis of rotation, which is also called the pivoted point. Okay. So the turning effect of a body depends upon the product of these two factors, and it is called moment of force or torque. Okay, so moment of force or torque is nothing but the product of the magnitude of the force and the perpendicular distance of the line of action of force from the axis of rotation. Okay, so from this discussion we can come to a conclusion that the turning effect of a body is the result of moment of force or torque applied on the body. Okay, students, let us now discuss about the measurement of moment of force or torque. As you have already discussed, moment of force or torque is nothing but the product of magnitude of force that is applied on a body and the perpendicular line of action of force from the axis of rotation. Okay, as you can see in this diagram, force is applied on point A. So this is the line of action of force. So what is the line of action of force? Line of action of force is AP. And if we draw a perpendicular from the pivoted point, that is point O, this is the pivot. Okay. So what would be the perpendicular distance then? OP is the perpendicular distance of the pivot from the line of action of force. Line of action of force. So what would be the moment of force or torque? So torque would be equal to applied force into the perpendicular distance of the line of action of force from the axis of rotation. Okay, so let us now discuss about the unit of torque. Okay, so students, unit of torque would be equal to unit of force into unit of distance, isn't it? So what would be the SI unit then? SI unit of force is Newton and that of distance is meter. Okay, so what would be the unit of torque then? Newton meter. Okay, this is the SI unit of torque. So what would be the CGS unit? CGS unit of force is dyne and that of distance is centimeter. So it would be the product of dyne and centimeter. But if force is measured in gravitational unit, that is kilogram force or gram force, then the SI unit would be kgf meter and CGS unit would be gf meter. Kilogram force meter and gram force meter. Okay, hope you understand. Students, the units of moment of force are related to each other. In this case, Newton meter is equal to, see, 1 Newton is equal to 10 to the power 5 dyne. Okay, and 1 meter is equal to 10 to the power 2 centimeter. So 1 Newton meter would be 10 to the power 5 into 10 to the power 2 dyne centimeter. Okay, so that would be equal to 10 to the power 7 dyne centimeter. Fine. Same way, 1 kgf, kilogram force. See, kilogram force equal to 9.8 Newton. Okay, 1 kgf meter would be 9.8 Newton meter. And what would be the value of 1 gram force centimeter? That would be 980 dyne centimeter. Okay, hope you understand. Students, let us now discuss about clockwise and anti-clockwise moments. Okay, so if the effect on the body is to rotate it anti-clockwise, then the moment is called anti-clockwise moment and it is taken as positive. Okay, and the effect on the body is supposed to rotate it clockwise, then that moment is called clockwise moment. Clockwise moment and it is taken negative. Okay, the moment of force is actually a vector quantity. Okay, when moment of Force is a vector quantity. Fine. The direction of anti-clockwise movement is along the axis of rotation but outwards. Same way, the direction of clockwise movement is along the axis of rotation but inwards. Okay? Students, we apply force on a pivoted body to rotate it. Okay? But the direction of rotation depends not only on the application of force or direction of application of force, but also on the point of application of force. Okay, as you can see in these diagrams, in the first case, the direction of application of force is same, but the point of application is different. That is why in the first case, the direction of moment is anti-clockwise, that means it is positive, and in the second case, the direction of moment is clockwise, that means negative. In the second diagram, as you can see over here, the direction of application force are different. Here the direction of application force is changed, thereby changing the direction of moment of force. So from this discussion we come to a conclusion that the direction of rotation depends upon the direction of application of force and point of application of force. Okay, let us now discuss some common examples of moment of force. Okay, the most common example of moment of force is the opening and closing of a door. Okay, while opening or closing a door, we apply force that is normal to the handle, where we actually apply the force. As you can see in this diagram, the force is applied on the handle, that means it is perpendicular force. Okay, and now what is happening? The distance of the handle from the hinge, that is where it is rotated, is the largest or longest distance. Students, you might have experienced that whenever we open or shut a door using the handle, we can do it comfortably. That means we use less amount of force. But what happens when we go closer to the hinge? Suppose we put our force nearer to hinge, as you can see in this diagram. So if we apply force nearer to hinge, we need much force. And if we apply force at the hinge, we would not be able to open or shut the door. Why is it so? Because at hinge, the torque would be zero. Why? Because we have already discussed torque is nothing but the product of force applied and the perpendicular distance. But at the hinge, the perpendicular distance would be zero. So torque would be force into perpendicular distance. So at hinge, perpendicular distance is nothing but zero. So torque would be force into 0, that would be 0. So what is happening over here? When we come away from the hinge, the perpendicular distance keeps on increasing. Okay, so if we are going for the production, if suppose this is A and this is B, A into B, suppose this is torque and is equal to A into B. A is the force and B is the perpendicular distance. Just try to understand this. Whenever B increases, what will happen with A? If B increases, we need to reduce the value of A so that we have a constant value, isn't it? So whenever it increases, force decreases. Okay? If the perpendicular distance increases, force needs to be decreased so that we can have a constant value. That is why when we try to open the door using the handle, as it is at the maximum distance from the hinge, we need less amount of force. Okay? Hope you understand. Students, when we drive a car, what we do? We apply our force on the steering wheel. As you can see in the diagram, when we need to change the direction of motion, we change it with the application of force on the steering wheel. But do we change the direction of force? No. We need not to change the direction of force. We just change the point of application of force. Okay. You can clearly see in this diagram that by changing the point of application of force, the direction of rotation of the steering wheel has been changed. Okay. Students, while riding a bicycle, we apply force on the pedals. And where is it attached? It is attached to a bigger size toothed wheel. And it is connected to the rear wheel. To rotate the rear wheel, what we do? We apply a small amount of force on the pedal and the bicycle moves smoothly. Why does it so? Because the toothed wheel at a greater perpendicular distance from the rear wheel. So as the distance is more, we need to apply less amount of force. Okay? Students, we can have many more examples like this which relates to moment of force. So from all these discussions, we can come to a conclusion that the moment of force doesn't only depend upon the magnitude of force applied, but also depends upon the perpendicular distance from the axis of rotation. That means the larger the perpendicular distance, the lesser the force that is needed to create or to produce the same turning effect, and vice versa. Hope you understand. Students, today we have discussed about the moment of force or torque. Hope you have understood everything clearly. If not, please watch the video again. Go through your book and read out everything. Just by attending a class or by going through the books, you cannot remember everything forever. So for that you need to revise again and again. So as I always say, keep revising, keep practicing, and most importantly, keep smiling.